Hello everyone, welcome back to lecture series on aerospace propulsion. So in the previous lecture, we were discussing about the different types of combustion and what are all the factors which is affecting the performance of our combustion chamber or design of our combustion chamber, and then how does the combustion process is happening, and what are all the how much amount of portion of air which is entering or splitting in the combustion chamber and entering in the different zones. Okay, so we have seen like in the combustion chamber hardly 12 to 13% of air is entering in the primary zone where the main combustion process is happening. Remaining all the air, out of that, almost 40% of your air is utilized or introduced in the secondary zone of your combustion, where the complete combustion process being completed, and remaining air is being used for the cooling purpose. Okay, so as you know that temperature released by your combustion chamber will be very high. So in order to avoid the high temperature rise, which will affect the turbines because of the material limitation, you have to limit the temperature of your flow which is entering your turbine. So we are diluting the flow temperature. So we have seen the different zones through the holes which is present in the liner, how the air is entering, and what is the purpose of this air enters at a different situation and all we have discussed in the previous lecture. Okay, so in today's lecture what we are going to discuss is that the chemistry of combustion. Okay, that is how the combustion is happening, or the chemistry behind the combustion process. Okay, and what are the parameters we use to measure the performance of our combustion chamber. Okay, that's what we are going to discuss in today's lecture. Okay, so let's start with the chemistry of combustion. What is the meaning of chemistry of combustion? In sense, what is actually happening in your combustion chamber? We are spraying the fuel, okay, and we are igniting it. So while igniting, we are burning our fuel. Basically, some sort of chemical reaction is happening. Okay, how does this chemical reaction is happening? How we are able to convert the energy stored in your fuel in the like a chemical energy form? How we are converting into thermal energy. Okay, so what is that we have to do, or what exactly is happening? That's what we are going to see in this chemistry of combustion. Okay, so you see, like this combustion process basically mainly depends on how effectively we are spraying the fuel or injecting the fuel. Okay, and how effectively we are mixing with the incoming air. Okay, you see, we stated that the combustion process is happening at in the range of Mach number 0.1 to 0.2. Okay, that means it's almost kind of like 80 to 90 meter per second. So in that 80 to 90 meter per second, hardly your combustion chamber is having length of say less than 1 meter. So that means we have a small space. In that small space itself, we have to spray your fuel such that it can properly mix with your incoming air, so that you can have the complete combustion process. If the mixing is not proper, what will happen? The combustion process won't be complete. You will have, instead of say carbon dioxide or nitrogen oxide, you will have the monoxide. So that is CO and NOs you will have. Basically, they are very harmful to your environment, as well as the incomplete combustion process will result in reduced efficiency of your combustion chamber. Okay, as such, so under what is the parameter which is basically limiting this combustion process, or what we have to take care so that the combustion process can be completed properly. That's what we are going to see in this section. Okay, so as we have stated, what is the function of your fuel injector? It is to spray the fuel in the fine droplet form. Okay, so that why do we have to spray the fuel in the fine droplet form? Because incoming air from your compressor, it's having certain amount of temperature. Okay, we are increasing the pressure across your compressor. Due to that, the temperature also increase. So when the fuel is injected in this hot gas, which is comes out of your like compressor, what will happen? Due to this temperature, your fuel will evaporate. So basically, from liquid it become gas. So when it become gas, it will easily dissolve and mix with your incoming air. If it is you are not going to inject your fuel in the fine droplet form, what will happen? It will take more time for the fuel droplet to evaporate. So obviously, the mixing won't be thorough. Okay, so in order to do the thorough mixing, you have to inject your fuel in the droplet form. Okay, so uh, even if you are going to inject your fuel in the droplet form, the reaction rate, that is rate at which your heat energy being released due to this combustion process, mainly depends on the what is the static pressure and static temperature inside your combustion chamber. Okay, so basically static pressure and static temperature depends on how much pressure and temperature of your flow comes out of your compressor. Okay, so this is an Arrhenius equation which basically states, okay, what is the reaction rate, or uh, the reaction rate is depends on what function. Basically, your reaction rate is directly proportional to pressure inside the combustion chamber and temperature inside your combustion chamber. Basically, what is P here is the pressure and T here is the temperature. Okay, so P and P power n, basically n is the exponents, basically depends on the number of molecules involved in the reactive collision. When you know that your air molecule is consists of different molecule, right? So here, when the you are injecting the fuel, that fuel is going to have different molecules. Okay, so based on that, you will have the collision rate. So for your hydrocarbon, okay, so you will have the value of n is equal to 1.8. Basically, which is constant, and f of t based on the temperature of your flow. Okay, the random motion of your molecule will change. That is, either your molecule will translate, rotate, or vibrate. Okay, so this f of t is basically a function of a temperature, and your p is basically pressure. Okay, so remaining E, R, T, everything is kind of E, energy available, and R is the universal gas constant. Everything is basically constant. So you could say your reaction rate is directly proportional to the pressure and the temperature. Higher the pressure and higher the temperature inside your combustion chamber will result in high reaction rate. Means easily you will have the combustion process. Okay. Now, as we have seen, if instead of that, if your pressure is less, means what will happen? The reaction rate become very slow. So how or when your pressure will become less? For example, in your sea level, your pressure is 101325 Pascal. Okay, which you will have the maximum. As you go higher and higher altitude, what will happen? Your pressure will be reduced. Okay, so if the inlet pressure itself is reduced, what will happen? The pressure delivered by your compressor will be reduced. That's why you are having each and every aircraft engine is having ceiling altitude, where that is you will have maximum efficiency. After that, if you increase the altitude, what will happen? It is going to affect the combustion process. Okay, that's why you can't fly like most of the aircraft you see commercial aircraft, we fly around 11 to 12 kilometer altitude. If you go above that, what will happen? You will have the thrust generated by your engine will be reduced. That's basically due to the limitation in the combustion process. Okay, so uh, here, if the temperature and pressure of your combustion zone or reaction zone is sufficiently high, what will happen? The reaction rate will be faster, and the fuel which is being evaporated also will easily come in contact with your oxygen. Obviously, you need oxygen for the combustion process. So when it come in contact with your oxygen, it will easily, you will have the easier combustion or proper combustion process. Okay, so for the fast or more acceptable, or to be precise, for the proper combustion process, if you are having a certain amount of fuel, you need to have a certain amount of oxygen. So without oxygen, you know that combustion process won't be complete. Okay, combustion one process will not complete means basically you are wasting so much amount of fuel, right? So what is this stoichiometric ratio here is basically it is the for example, if I have a 1 kg of fuel, for burning this 1 kg of fuel completely, okay, how much amount of kg of air I required? That's what we call it as the stoichiometric ratio. Okay, so that is you are having a CH4. Basically, it is the most commonly used hydrocarbon fuel. So in that CH4, when I add the air and if I do the combustion, what will happen? This CH4 will be converted into carbon dioxide as well as water vapor. So if I have a 1 kg of this fuel, okay, it should be completely converted into carbon dioxide as well as water vapor. For that, how much amount of air I required, that's what we call it as the stoichiometric ratio. Okay. So as you know that your atmosphere air consists of 23% of oxygen by mass. Basically, if you talk about in terms of volume, you'll have like only 21% of air is having like out of 100% of air, you will have only 21% of oxygen. But if you talk in terms of mass, since the mass of your oxygen molecule is more than your nitrogen as well as your oxygen, sorry, nitrogen as well as your hydrogen, your mass percentage is basically 23%. Okay, so since not your complete 100% air is made of oxygen, only 23% of mass of oxygen is made up of your oxygen. So you need to calculate the what will be the amount of uh, air required to complete the complete combustion process. Okay, so say this equation is the overall complete combustion equation. For example, I have an hydrocarbon, let's say CaHb. Okay, so CaHb, in that A and B may vary based on your what type of fuel you are going to use. Okay, for this, I need to add, say we have oxygen, okay, and nitrogen, sorry, oxygen and nitrogen in your air. So how much amount of air you need to do the complete combustion process is that basically A plus B by 4 into O2 plus 3.773 into N2. Okay, so basically this is the air. This portion is basically your fuel. This is your air. So when I have this much amount of air, your complete combustion will occur. That is, A number of CO2 will be formed and B by 2 number of H2O will be formed, and remaining will be nitrogen or nitrogen monoxides. Okay, so here, as you can see here, the molecular weight of your oxygen and nitrogen and carbon and hydrogen are basically your oxygen is having maximum value which is 32, and after that you have the nitrogen molecule which is having molecular weight of 28, and you have the carbon which is having 12.011, and the least among these is hydrogen which is having 1.008 mole per kilo. Okay, now we have like the molecular weight of your different molecule. So from that you can calculate how much amount of air required, or what is the stoichiometric uh, air fuel ratio or fuel air ratio. Air fuel ratio means mass flow rate of air divided by mass flow rate of fuel, or fuel air ratio means mass flow rate of fuel divided by mass flow rate of air. Okay, so this stoichiometric equation we have seen right previously. So if I want, as you can see here in this, what is your y is basically it is b by a. Your y is b by a. So how do I find out the fraction of mass fraction? Means basically you should know what is the mass of your fuel and mass of your air. How do I calculate? Based on the what to say, your atomic weights or molecular weights, you can calculate what is the mass of your fuel and mass of your air. So here I stated y is equal to b by e. Okay, so in this first, let's say it is air fuel ratio, you have to find out what is the mass of your air and what is the mass of your fuel. Okay, so how do I calculate? You see in this equation, if I'm going to take a as common, here also a as common, what I'll have, you will have, if I'm going to take a as common, you will have 1 plus b by a. Basically, you will have 1 plus y by 4. That's what, 1 plus y by 4 into what is the molecular weight of your oxygen? Basically 32. 32 plus 3.773 into molecular weight of your nitrogen, that is 28.16. Okay, this divide by, what do you have? Carbon and hydrogen. So carbon C, okay, 12.011. We have taken A as common, so you will have here B by A. B by A means basically HY, that is 1.008 into Y. This B and A is depend on what type of fuel, hydrocarbon fuel you are using. Okay, so from this we can find out, if I'm going to simplify this equation, we'll get this 3.56 into 4 plus y divided by 12.011 plus 1.008 into y. So as long as I know what is my fuel which I'm going to use, from that you can calculate y, and for that fuel you can find out what is your air fuel ratio. If you take the inverse, that is going to give you fuel air ratio, that is stoichiometric fuel air ratio, that is the minimum amount of air required to complete the complete combustion process. So as long as we know, you can find out what is, like for example in your when we seen the when the airflow entering inside your combustion chamber, we have seen the snout like segregates or separates your flow into primary and secondary air. The secondary air is going through your space between your liner and casing. Your primary air is passing through your this swirl veins, right? So there you are seeing only 10 to 12% of air we are sending, because only that much amount of air is required to do the complete like combustion process. That is the stoichiometric fuel air ratio. Okay. After that, what we will do is that we will inject or we will send the remaining air for the cooling purpose. So you could think that if 100 kg of air is entering inside your combustion chamber, hardly 20 kg will be used for the combustion process. Remaining 80 kg is being used for cooling alone. Okay, you should not think we need that much amount of air for the complete combustion process. So only portion of air is being used for the combustion process. Remaining air is being used for the cooling of your combustion chamber. Okay. So next one is we are going to discuss about the combustion chamber performance. So combustion chamber performance, basically, you know what is the purpose of your combustion chamber? It is to convert the energy stored in your fuel into thermal energy. Okay, that is, or to burn your fuel completely for a wide range of operating conditions. Wide range of operating conditions, irrespective of whatever happening to your inlet condition. For example, if the atmospheric pressure is changing or your aircraft speed is changing, okay, whatever is happening, it should complete the combustion process without much of total pressure loss. Okay, so how do we measure or how do we say whether my combustion chamber is performing better or not? So what are all the evaluating parameter, or how do we evaluate the performance of your combustion chamber is based on these three parameters. Basically, they are pressure loss, combustion efficiency, and combustion stability. Okay, so you should have all these three values, three parameters should have significant value, so that you can say whether your combustion chamber, because see, you design an combustion chamber, how do you know that whether this combustion chamber is performing better or not? Is you have to do this, you have to find out what is the pressure loss happening in that combustion chamber, you have to find out what is the how effectively the combustion process is happening, and what is the stability range of that particular combustion chamber. So these three parameters you measure, that is going to tell you whether the combustion chamber which you designed is performing better or not. Okay, so let's start with the pressure loss. Okay, so what is the pressure loss means? You know that in aerodynamics, whenever an airflow is moving over an any solid surface, there is going to be a, you know that your flow or fluid is viscous in nature. When the viscous fluid is moving over a solid surface, you will have the boundary layer growth. Okay, the boundary layer growth will result in frictional loss. whenever there is going to be a frictional loss, what will happen? That is going to create the total pressure loss. Okay, so total pressure loss is happening means basically the energy available in your flow, which is basically in the form of pressure, is being converted into some other form which you are not able to utilize it. That's what loss. That's the loss happening inside your combustion chamber. So this pressure loss should be as minimum as possible for your combustion chamber performance to be better. Okay, so what are the sources of these combustion chamber pressure losses? Are maybe there may be two sources. One is cold flow loss, another one is the hot flow loss or fundamental losses. So what is this cold flow loss and what is this hot flow loss? In sense, you see, when your flow is entering inside your combustion chamber, we have a diffuser, right? So the purpose of your diffuser, you know that it is to reduce the incoming flow velocity. Okay, since there is an expansion here, or if there is going to be an expansion, okay, in sense here your pressure is being increased. When the flow is passing through this divergent section, your pressure will be increased, and that will create a boundary layer growth. Basically, it is adverse pressure gradient, which is easily lead to flow separation. If there is going to be a flow separation, you will have the loss, that is total pressure loss. Okay, since there is a presence of solid body, not only this diffuser section, next you have these snouts or flow is passing through the spacing between your liner and casing. Your flow is entering at different stations, right? So because of this, when the cold flow is moving over these solid surfaces, what will happen? There is going to be a significant loss in the total pressure. That loss, what we call it as the cold flow loss. Okay, that is due to the viscous nature as well as the turbulent nature of your flow, because we introduce the turbulence in your flow field in order to thoroughly mix your fuel and air. So since we are introducing the turbulence, okay, that will obviously lead to some amount of loss. Okay, so without doing any combustion, if I simply send this cold flow inside my combustion chamber, how much amount of pressure loss is happening? That's what we call it as the cold flow loss. Now, what is this hot flow loss or fundamental loss? In sense, you see, when we do the combustion, what will happen? Your temperature is getting increased. As you know, for your air, if the temperature is increased, its viscosity will increase. The viscosity increases means the loss due to friction also will increase. So basically, what is its fundamental loss is that when the temperature of your gas is increased due to combustion, how much additional loss is happening? That's what we call it as the hot loss or fundamental loss. So we can say that pressure loss factor PLF, which is equal to basically it is summation of cold flow loss plus hot flow loss. This K1 is something to do with cold flow loss and K2 is something to do with the hot flow loss or fundamental loss. So you see, if you compare the magnitude of loss, okay, your cold flow loss will be very high compared to that of your hot flow loss. So that whenever you are designing, for example, you have a fuel injector inside, you have the liners. So the cold you should try to reduce the cold flow loss by designing your combustion chamber properly. You can try to reduce this cold flow loss. Okay, because hot flow loss you can't do much because you have to increase your temperature. And same goes for magnitude is very small compared to your cold flow loss. So the main thing you should focus is how we can reduce the cold flow loss. Next one is the combustion efficiency. Okay, so what is this combustion efficiency in sense? How effectively when I do the combustion, how do I transfer the energy inside your fuel into your incoming airflow? So we are heating, right? Basically, by doing the combustion, I'm increasing the temperature of my flow. So what is this combustion efficiency? Basically, it is the enthalpy rise during your actual process divided by enthalpy rise during your ideal process. Okay, so during your ideal process, obviously the enthalpy rise is going to be more than your actual process because of some loss. Okay, obviously the enthalpy rise during your actual process is going to be less than the enthalpy rise during your ideal process. Ideal process means complete combustion process is happening. All the energy available in your fuel is converted into heat energy. But when you go for, do see an actual process, it may not have an 100% combustion. So that will lead to certain amount of loss. So the ratio between the enthalpy rise during your actual process divided by enthalpy rise during your ideal process, what we call it as the combustion efficiency or burner efficiency. Basically, you can write this in terms of mass flow rate of your fuel. Okay, in sense, for example, if you are rising a certain amount of temperature, okay, say for example from 500 Kelvin to 1500 Kelvin, you have to rise your temperature. Let's say for that I'm burning 1 kg of fuel. Okay, so let's say what is this combustion efficiency? In sense, how much amount of fuel I need during your ideal process to rise your temperature from 500 to 1500 K. Okay, divide by how much amount of fuel you need to have during your actual process. Obviously, during your ideal process, the amount of fuel you need to have or you need to burn will be less than the amount of fuel you need during your actual process, because during your actual process the enthalpy rise is less than your ideal process. Okay, so this is what we call it as the combustion efficiency. And last one is combustion stability. Combustion stability means basically it is the up to what range, okay, you can do the stable combustion. That's what we call it as the combustion stability. So your combustion chamber you designed, okay, uh, like you have found what is the loss happening, and you got the combustion efficiency. One more parameter it's very important, that is it should have a wide range of combustion stability, or for wide range of operating condition the combustion process should be stable. This is a very important parameter, because even if your efficiency is maximum, even if the loss happening inside your combustion chamber is very less, if the operating range, okay, for the stable combustion is small, means which is going to limit the application of that particular engine. So when you are designing an engine, that combustion should be stable for a wide range of operating condition. Okay, so we have seen, right, air fuel ratio. So this air fuel ratio, we have something called lean mixture and rich mixture. Okay, what is a lean mixture and what is a rich mixture? Means lean mixture means where the mass flow rate of air is more, or the air fuel ratio is high, whereas rich mixture means air fuel ratio is less. Okay, so there is a range for this air fuel ratio. Okay, that is rich limit to weak limit, within which your combustion process will be stable. If you go beyond that, what will happen? Your combustion process won't be stable. For example, if the air fuel ratio is keep on increased after a certain limit, what will happen? The air fuel ratio becomes very high, the amount of heat released, okay, will be very less, because your airflow is very high, okay, which will lead to what will happen? Extinguishing of your flames. Once your flame is extinguished, means what will happen? You won't have the self-sustained combustion process. Instead of that, let's say if you are going to pour too much amount of fuel, which will reduce the air fuel ratio, even the too much amount of fuel will lead to improper combustion or incomplete combustion. That also may lead to the extinguishing of your flames. Okay, so you can't have very lean mixture or you can't have very rich mixture, but the range between your lean mixture and rich mixture should be very wide, so that you can have the wide range of operating condition. Okay, so this is a graph which states the combustion stability limit of an any combustion chamber. Okay, so as you can see here, the this is basically rich limit. So basically your air fuel ratio is very less. As you increase the during your rich mixture, if the airflow mass flow rate is increased, means what will happen? The range is getting reduced, because you know, for the flame which is generated inside your combustion chamber, which is having something called flame speed S. Okay, so in simple layman language, what is this flame speed engine? For example, um, you might have seen like you are having burners, right? Okay, or let's say take yeah, burner in your house burner up to certain speed. If you are blowing an air, it won't be extinguished. But if you are sending a very high speed air towards that flame, what will happen after certain velocity, or for the certain speed of your airflow, the flame will be extinguished. So same, what is this flame speed in sense? What is the maximum temperature, sorry, velocity up to which you will have the stable flame inside your combustion chamber. Okay, each flame generated by a particular type of fuel will have something called this flame speed. Okay, so when the airflow mass fluid is increased, basically the velocity of your flow is increased. What will happen? It is going towards that velocity of your flow is going towards the flame speed. That's why it is narrowing the range at which you will have the stable combustion. If you're having the mass flow rate within this limit, okay, and the air fuel ratio also within this limit, means you will have the complete combustion or stable combustion. If you go out of this range, what will happen? The combustion process won't be stable. Okay, so this range should be wide enough for your combustion chamber, so that you can have the even under different adverse condition, you can have the proper or complete combustion process in your engine. Okay, so these three parameters are very important. One is your pressure loss, it should be minimum, combustion efficiency should be maximum, and the stability limit also should be as much as possible in order to have the wide range of operation for your aircraft. Okay, so with this I'll complete today's lecture. So what we have seen the mechanism of combustion, okay, and how we can find out the stoichiometric fuel air ratio or air fuel ratio. Okay, so for the given type of fuel, and then we have seen the what are all the parameters we use to measure the performance of our combustion chamber.
Like, share, and subscribe. Hit the bell icon for more updates.